2637 kernel. What better way to start a new year than with a new kernel? This was a fairly big release with well over 11,000 change sets in it. This kernel brought in the first of a set of scalability patches for the virtual file system layer, which added a fair amount of complexity to that layer, but also, if you had the right kind of workload, brought about something on the order of 30% performance improvement. You're doing lots of opens and closes, that sort of stuff. So that was good to have. We got the block I/O bandwidth controller, it's actually the second bandwidth controller working at a higher level in the I/O scheduler stack, allowing the placement of absolute limits on block I/O bandwidth. Finally got some support for the point-to-point tunneling protocol in the mainline kernel, basic support for the parallel MFS protocol, and wake-up sources, which is an interesting. In some of the wake-up sources, is just an accounting mechanism for tracking devices in the system that can wake the system from a sleep state. But as part of a bigger effort to replicate the Android opportunistic suspend mechanism and provide an implementation of that mechanism that works well within the mainline kernel. So we're still seeing pieces of that going in, pieces of it that are under discussion, but at some point we may actually have a solution for that. So that was 2637. A lot went in there. And a lot has happened since then. So what has gone on since 2637? We've made 5 more kernel releases. I'll kind of call them out as they come in going around the year. We've merged almost 60,000 change sets over the course of the last year. There's over 3,000 developers. And at this point, we have over 400 companies that we can identify that have contributed to the kernel. So I've put up numbers like this before. We've seen them before. We know at this point the kernel is a very active, very fast-moving project. Perhaps the biggest on the planet, hard to say. And it continues to move on and shows no real signs of slowing down. So February of 2011. One of those things that happened early on in February was a little note that came out from Greg Crow-Hartman, congratulating Redwood, saying, as you can see, Redwood has stopped just dumping drivers on us and instead is now working on patching the driver that we already have in the upstream kernel and trying to make that driver support the new hardware. This, he said, shows a huge willingness to learn how to work with the kernel community, and they need to be praised for this change in attitude. This is, I mean, it's a nice note, but there's nothing all that special about it in a way. It's something that we go through with a lot of companies where they take a little while to figure out how to work with us, and then they do. And so we see a lot of progress as companies figure out how does the mainline kernel process work? How can we get our code in there? Why is it in our interest to do so? And then they figure out how to do it, and then we just become part of the machine. And we see this happening over and over again. So this seems as good a time as any to put up this slide. This is a variant of a slide I've been making for a while, showing the top contributors to the kernel over the course of the last year, from the beginning of the 2638 development cycle through the 3.2 release. So we see, as always, volunteers, top of the list, just under 14%. There's of change coming in from people working in their own time has actually slowly fallen over the years. And why that is hard to say. One could take a pessimistic view and say the kernel is getting too big and too complex. The easy projects are done, and so we're putting off our volunteers that way. On the other hand, one could look at this and one could say, well, anybody who's shown any ability to actually get code into the kernel in any kind of reliable way tends not to stay a volunteer for very long unless they really, really want to, because they tend to get buried in job offers. So that, of course, is not going to be a bad thing. Other than that, we see a lot of the same companies we've been seeing for quite a long time. We see companies that not only are competing fiercely in other areas of the market, but in fact, at this point, they all seem to be suing each other elsewhere. But they're still working together quite well at this level. And the situation hasn't changed a whole lot. There's one change I want to call out. This is one. All right? We'll do it the old-fashioned way. Or we won't. Speak to me. Come on. All right. Well, this is the one I'm going to get to eventually. At this point. All right. We'll get there. Never done that before. All right. This is just a plot of the percentage contributions from the top companies. Say companies we saw on the last slide. And what we see is in a very noisy sort of way, we have horizontal lines. Right? The companies that were contributing back around 2620, which is when this slide starts, are still contributing heavily now. The big change I want to call out is those two heavy lines at the bottom. Those two lines correspond to TI and Samsung. Right? And they correspond to a trend that we're seeing in general, which is a much increased level of involvement from the mobile and embedded community. As mobile Linux grows in importance and grows in deployment, these companies are figuring out that they need to work with the mainline, and they're doing so. And so we're seeing this very strong upward trend in contributions from that part of the market. I think we'll continue to see that quite simply. One other thing that happened in February, just to point out quickly, this didn't actually happen then, this one kind of came out and became well known. Red Hat, from their enterprise kernel, stopped shipping individual patches with their kernel, and now you just get one big blob with all of their changes, all 7,699 changes in their current kernel, kind of mixed in together into a single thing. So it's become much harder for people who want to look in there and see what are the individual changes that Red Hat has actually made to the kernel, and why have they done that. And that's kind of a sad statement on the nature of the competition at that level of the marketplace. And there's not much to be done for it. It is, of course, entirely compliant with licensing and so on. But it's not something that is really welcome. All right, let's move on to March. Well, another month, another kernel release. That's when 2.6.38 came out. A couple of very interesting patches that came out then, including per session group schedule. This is the famous 200-line kernel patch that people were talking about for a while, that turned into about an 800-line kernel patch by the time it actually went into the main line, that allows the kernel to employ the group scheduling mechanism automatically and partition processes into different groups and schedule the groups against each other. This can give you much nicer interactivity in desktop situations. It's useful in a lot of other situations as well to keep different groups of processes from interfering with each other in the scheduler. And the nice thing about this particular patch is not that it added this feature, because we've had this feature for years. It sort of made it just work. There's a whole lot of nice things that we have in the kernel that people don't really make a whole lot of use of, because you have to be fiddly think with them to make them work. If you can make them just simply work for people, then things are a whole lot better. Transparent huge pages, which is also on the list, is another example of that. The huge page mechanism in most processors allows memory management units to work with much larger pages. You get a nice performance improvement out of that for just about any workload you can think of, because you save a lot of pressure on your translation with the side buffer and such. Transparent huge pages used to require you to set up huge TLDFS to the side, make changes to your application to make use of it, and so on. So there weren't too many people actually using it. Now we're all using it because it simply works in the system, and we all get the benefits from that. So we have various other things, including the other half of the virtual file system scalability patch that I mentioned before. Transmit packet steering, which is a networking scalability change that came out of Google, and improvements to the blockout bands controller, and of course a whole bunch of other stuff. But it's those two patches that I think were really the significant features of 2.6.38. Something else that happened in March was it leads to a temper tantrum. This is not necessarily all that surprising, it happens, but this was a fairly big one. He got a bunch of pull requests from the ARM community, and he decided that he was really just fed up with them. And so he stopped actually pulling them and said, okay, somebody needs to get a grip in the ARM community. So what's going on here? I probably don't need to tell the people in this room that the ARM architecture is interesting, and it doesn't really come with a platform definition the way some other architectures do. Every ARM system is unique in its own very special way. And so there's a lot less commonality in terms of the code needed to support those systems. When I say the embedded mindset, what I mean is that we have a lot of people working on their own special little projects, working usually under very intense time pressures, and so on. And so they've tended to solve their specific little problem. And if they put their code upstream at all, they've worked in their own piece of the tree and not really thought about making the kernel better for everybody involved. So we've ended up with a lot of stuff. There's really been nobody overseeing this tree to try to make this better. So we get lots of little subtrees with a lot of duplicated code and a fairly big, ugly mess that has resulted in that tree. Another way of putting this is that for years we have been asking the embedded community, contribute back to the kernel. Please, give us your code back. And the fact is they're now doing that. Right? What we have here is a problem as a result of our own success. We've gotten what we wished for, and you should always be careful what you wish for. But in fact, what's happening is really a good thing. And the only real problem is that we haven't developed processes within the community to actually manage all of this stuff. So what's happening, we're trying to clean things up. There's more higher level oversight now. ARM is running a tree that funnels a lot of the system on chip stuff into the kernel, and so on, trying to keep a better grip on it. There's a lot of cleanup work going on at various levels, consolidating code that was duplicated across all the various different ARM sub-architectures, and a move towards the device tree mechanism that can hopefully someday help us get rid of a lot of these word files and such. And maybe someday, I doubt we'll ever have a single kernel that runs on every ARM system, but we can maybe have a kernel that runs on a lot of the more popular ones, without having to build specifically for whatever system you're working on at any given time. We're heading in that direction. Things are getting a whole lot better. And ARM is not only becoming a proper first-tier architecture, it's actually starting to drive things in interesting ways. If you look on LWN today, we just posted an article from an ARM developer about a concept called big.little. We've got a system on chips now that have two different classes of ARM processors on them. There's the big, fast, power-hungry one, and the little slow, power-efficient one. And you're trying to figure out which one of those you should be using for any given workload at any given time. This is going to stress the scheduler in very interesting ways. The scheduler has not been written with that kind of stuff in mind. So we now have stuff coming up from the mobile embedded world that's really going to be driving the future directions of the core kernel. And it's going to be very interesting to watch. All right, moving on. April. That's what April looks like in Utah. Nice place, although the network connectivity is kind of poor. But you got to take it. So we had an interesting fight that came about in April as a result of the posting of a thing called the Embeded Linux KVM tool. This is just a small replacement for QEMU. It's a hardware emulator aimed mostly at kernel developers who don't want to mess around with a big, fully functional sort of system. The sticking point is that they wanted to merge this code, which is user-space code, into the kernel source tree. So we've had people actually pushing this idea pretty hard. This is Ingo Molnar. Somebody is going to integrate all of this stuff together in a single tree and make the killer distribution, which is everything else aside. So not everybody agrees with this, needless to say, but this is an idea that's being pushed. The people who push the idea of putting kernel or user space code in the kernel tree set a number of advantages. The code becomes a whole lot more visible when it's in the kernel tree. You can patch it and end up in the kernel change. A lot of people like that. So you tend to get more developers. They say you can develop the kernel API and its users together. So the two can develop into a much sort of more homogeneous whole, and encourages developers to think across this kernel user space boundary, which is a pretty hard boundary that people usually work on one side of or the other. And the idea is you're supposed to get better integration across the whole system if you do this. On the other hand, people complain that it makes the kernel tree bigger. The kernel tree, the source tree, is not all that small now. There are claims that you get API stability problems, because if you can change a user space API and its primary user at the same time, as you got them all together in the same tree, you can, in theory, create stability problems for other users of that API. This is not supposed to happen. We're not supposed to do that in the kernel. But there are people who claim that this does happen. They claim that out-of-tree projects are disadvantaged because they just don't get the same sort of visibility. And they ask, where does it end? Do we put our desktop environment into the kernel tree? Do we throw LibreOffice in there? You never quite know what's going to go on there. So this is a fight that's going to go on for a while because these people are not going to give up on this. Linux seems to be kind of holding the line on pulling more user space stuff in for now. But I don't think we're done with that discussion. One other thing, sorry Mark, wherever you are, but this was a quote that really stuck me at the time. That for all of the progress we have made about getting companies to work with the development process, we still have pockets of resistance where they say we need to work with proprietary drivers and binary-only code. And this is something we've been fighting for years. In the end, it seems like we almost always when companies figure out that it is not in their own interest to ship their code this way. But it continues to happen. And we're seeing it certainly in the mobile area now with graphics drivers and some others. And I hope that once again we can get past this and get to where we have truly free platforms so we can working on it from the bottom. Alright, moving on to May. One thing that happened in May was the posting of a mechanism called secure computing, or an enhancement to this. The idea here was to add a feature where a process could install a bitmap in the kernel, saying only the system calls that are indicated in this bitmap will be accessible to me from here on out. It was meant for use with the Chromium browser to, as part of their sandboxing scheme, just trying to reduce the attack surface of the kernel. To take a whole bunch of system calls that they know they won't use and just take them off limits so they cannot be accessible. So people look at this and they say, okay, cool. But how about if we enhance this a bit? We can add a filtering mechanism. We can maybe hook it into the trace point mechanism because we've got all these points already in the kernel. At which point the trace point people jump in and say, well, wait a minute, you're not doing that to my trace points. And the big fight results. And in the end result, after the dust is settled, nothing gets merged and the developer goes away. So one can find this and can say, okay, this shows the kernel development process at its absolute worst. Right? We had this big fight, and we had a promising young developer trying to do cool stuff who got discouraged because people tried to throw their own irons in the fire, and nothing happened. On the other hand, last month or so, he came back with a completely reworked version of this patch using the Berkeley packet filter, which works a whole lot better. It's a much nicer design, and it looks like it probably will go into the kernel, perhaps as soon as 3.4. So one can say, in fact, this shows that we did things right, that we push back on things until we get something that suits us, that solves the problem correctly, and we wait until we get the right solution in there. So, you can interpret it either way. Also, we had yet another kernel release in May when 2.6.9 came out. Various interesting sorts of additions, including directed yield, which is a virtualization optimization ID set, the mechanism for managing large numbers of IP addresses in the firewalling mechanism. Transcendent memory is an interesting approach to memory management, used again mostly in the Xen area at the moment. The core ones at this point, not the users of it. User namespaces are part of the solution to the containers problem. Containers can be thought of as a form of lightweight virtualization where you wall off a group of processes, but they're all running on the host kernel. Right? You're not running on a virtual machine, you're running on the host kernel. This is actually a much harder problem to solve than full virtualization is. They've been working on it for many years, and they will continue to be for a little while yet. We've got another one of the pieces in there. The media controller is a response to hardware complexity. We've now got, in this case, video acquisition devices, webcam devices, or even your phone camera devices, that now have multiple hardware components. You're trying to patch the data between them in various sorts of ways and export an interface to user space that actually allows this to be used. This is complex stuff, and I don't think we've actually solved this problem very well yet, but we're trying to do our best. One other nice thing that happened in May. Thanks to Arn, who really carried that one across the finishing line, although a whole lot of people worked on it to get it there. Given enough time, we can solve just about any problem we have to. So we got 2.6.3.9 out, and then Linus started hearing voices, right after that, during the merge window, saying, the numbers are getting too big, and maybe he's going to call this thing 2.8.0, because when the voices speak, he listens. So, of course, when you say something like that, one of the first things that's going to happen is you're going to get more voices. So Greg Proharman comes out and says, well, if you do this, I'm going to buy you a bottle of whatever whiskey you want. Well, it must have worked because, of course, as we all know now, Linus did this. He didn't call it 2.8.0, he called it 3.0. This was, as I think pretty much everybody knows at this point, just a numbering change. There was nothing particularly special about the 3.0 kernel that merited a major number change. It's just that we were getting really, really tired of these big version numbers. So we went on from there. So the week after that, Greg did in fact present him with a bottle of whiskey on stage with cups. He didn't open it, although what happened later that evening was not necessarily well advised. And so we now have 3.x kernel series instead of 2.6, and everybody is happy ever after, at least until we get to 3.something big. Alright, in June we saw another posting of an interesting feature for the ext4 file system, being the snapshotting feature. Snapshots, of course, are a nice feature. You save a copy of the state of the file system at some particular point. You can use it for things like rolling back from a failed system upgrade. You can use it to create a quiescent version of the file system for backups. You can also actually make use of a feature like this in an embedded device or factory reset kind of functionality, where you simply have a snapshot being the initial factory state of the device. All you got to do is go back to that snapshot, and you've done a reset. So, nice feature, everybody likes it, but we still had some complaints about it. This keynote was posted by Joseph Bassett, who was a ButterFS developer. And he's saying, well, why is it that we're shoehorning these big features into ext4, which is supposed to be a stable file system, right? Meanwhile, we've got ButterFS that already does all this stuff, and we're trying to stabilize it. So, other people have asked very similar questions. Why are we doing stuff like this to ext4? When ext4 was meant to be our stopgap until the real next generation file system came out. Well, as it happens, there's an awful lot going on with the ext4. With 3.2, we said the addition of a significant feature called Big Alloc allows it to finally move away from allocating blocks in 4 kilobyte chunks, and you can allocate much larger chunks. If you've got a file system that's mostly holding large files, then what you end up with is much more efficient operations on those files. So this is useful within Google, for example, where they're trying to do this, where a lot of the driving force of this came from. And other places as well. It's a significant speed up. And we've got various other things in the works, including the snapshot feature that I mentioned, inline data, which is optimization for the sort of very small files, secure erase, so that if you delete a file, it actually goes away from the media completely. Protects on your metadata, trying to defend against corruptions on the media itself, and so on. So what's going on is that ext4, rather than just sort of sitting there and gathering dust and fading away, looks to develop and grow for quite some time yet. Because there are people who are adopting it and using it, but who want to deal with this stuff with it. And so as long as people keep hacking on it and adding new features, that stuff's going to go in. I don't think ext4 is going to kind of fade away anytime soon. Also in June, people started talking about this thing called UEFI Secure Boot. The objective of this feature, of course, is to create hardware that will only give control of the system to a trusted bootloader. This is a bootloader that has been signed by a key that is known to the system level BIOS. It's actually a useful feature. You can use it to thwart attacks on the BIOS or on the bootloader of the system, very low-level rootkit type stuff. And it helps you to ensure that the system is running what you think it is. There is, of course, just one tiny little nagging problem to this thing, which is who is trusted, right? Who do you trust? Is it the person who thinks they actually bought a computer? Or is it the person who sold it to them? Is it the person who put the hardware onto it? Is it the entertainment industry? All of these people are making a play for control over this and to be the trusted party who says what you can actually run on your computer. So UEFI Secure Boot is another of these mechanisms that could result in the loss of control over our system, something that we have been fighting for years, and we have been gaining. We have a whole lot more open systems than we have had in years. I think the situation is nice and getting better. And this could take things the other direction. So what's going on? There's, of course, been a whole lot of work to call attention to the problem. White papers have been written, blog postings have been posted, so on and so forth. And some concessions have actually been gained from all of this, including the understanding that any x86 system that you buy can be put into the setup mode. This means that for any of these systems, the user can not only boot whatever system they want on there, but they can actually install their own keys and boot whatever system they want in the trusted mode, which is useful. They can actually make use of this capability if they want to do so. It will be possible to install your own signing keys. But there's a few little glitches still. Installing that key may not be easy. In fact, it's going to have to be done at a low level. So users wanting to do this are going to be entrusting their lives to the user interface development skills of BIOS engineers, which seriously may involve typing in big long keys as big long series of text digits and so on. This is not going to be fun. Okay. There's no provision at all for booting from CD in a trusted mode, so live CDs could be a thing of the past. And I've put down here that ARM systems can be totally locked down. In fact, if they're going to meet the Windows labeling requirements, ARM systems must be totally locked down. It's not just that they can, it's actually a requirement that they be done in that way. And that, of course, is not what we want to see at all. So there's a lot to be done in this area still. We're going to be fighting about UEFI and its successors for a while. All right, moving on. In July, one of the things we saw was the first version of the real-time patch set to come out since March. The real-time patch set had been stuck on 2.6.33, and users had been stuck there for a while, much to their chagrin. It wasn't what they wanted. They ran into some pretty gnarly technical problems that kept things from advancing for a while. But we finally did get a new version in July. So where does the real-time patch set stand at this point? Well, of course, we get very nice determinism out of it if you have the right hardware at this point. If you don't have the right hardware, you still lose. There's not much to be done about that. One of the most thorny problems with this has been the problem of per CPU data. Per CPU data is one of the most significant scalability techniques that's used on larger systems. But does not really work very well in the real-time world. It's not good for determinism. So they come up with a solution that involves some fairly scary locking assumptions. So locking assumptions tend to be scary in general. So they're designated as such. They're really scary. So this is going to have to be watched for a while. But the plan is to merge a lot of the real-time tree in the next year. We will see, but this group of people back in October at the Real-Time Mini Summit did in fact kind of partition this stuff and do it. I know Steve's been rushing right out to merge that stuff. And so on, so we'll see how it's coming along. There's still a couple of open issues, one of which is deadline schedule. There is actually a pretty nice deadline schedule patch out there, but the developer who is working in that seems to have gotten distracted by other things. We haven't seen a revision of that for a while. Somebody else may have to pick up deadline schedule before we actually do. Somebody else does? Oh, cool. I haven't seen that yet. And there's a lot of interest in CPU isolation, where you take one or more CPUs on the system, and you say, this is only going to run the application. No interrupts, no operating system, nothing else, just the application. So there have been various proposals for how to implement that. People are working on that, and we will perhaps see a solution to that emerging over the course of the next year. We will see. Also in July, as we were coming around the 3.0 release, all of a sudden it got delayed. It got delayed to the point that it pushed the merge window in the middle of vacation, which is not something he wanted at all. It became a little grumpy. But we had this bug in vulnerability patches that would cause files to just sort of disappear for a little while. And disappearing files are just not one of the things that was on the feature set for 3.0. So we had a fairly high-profile debugging crew, being Linus Torvald, Alviro, the chief BFS maintainer, and Hugh Dickens, arguably the top memory management developer. And it still took them about a week to figure this out. It was a really subtle and strange bug, which drives home a point that some people have been making for a while. Some parts of the kernel, especially the core kernel, have reached a level of complexity that is truly daunting. It's really scary. Trying to go in there and figure out what is going on. I'm not sure there's anybody who really understands it all anymore at this point. And I don't know how you fix that. But that kind of complexity is the sort of thing that can kill operating systems over the long term. So we need to really think about how it is that we can, if not get rid of some of this complexity, at least keep it from getting worse. Yeah. We will see. Anyway, despite that, 3.0 did come out towards the end of July. So we had some new POSIX clocks for waking from suspend and all that. We now have a just-in-time compiler built into the kernel for the Berkeley packet filter subsystem packet, for filtering packets that you're trying to inspect from the off and that sort of thing. Send multiple message system call, scalability for applications that are sending lots and lots of little messages. ICMP sockets, so you can write an unprivileged ping client that lasts namespace file descriptors, another piece of the containers problem, allowing the system administrator to move into and out of containerized systems, and clean cache, which is some of that transcendent memory stuff that I was talking about before. It's a different way of caching pages and such in the system. And that was our 3.0 kernel. In August, went to Taipei and got a lesson that certain aspects of hacker culture really don't change no matter where you go. It all comes down to pizza. And Europe, of course. We had a discussion about an API called X32 in August, which is an interesting approach to 64-bit computing. 64-bit mode is, 64-bit processors are very nice things. do a lot of stuff. You can address vast amounts of memory and all of that. You really want to run your kernel in 64-bit mode if you can. But as it turns out, very few applications actually need either 64-bit data or 64-bit pointers. So for these applications, expanding all that stuff out to 64 bits is really just bloat. You've expanded your application quite a bit. That will slow it down, of course, and use more memory. So that's what you want. So the response to this is the X32 ADF, where you're running your processor in a 64-bit mode, but you're using a restricted set of instructions to deal in 32-bit data. So you're dealing in 32-bit data, 32-bit pointers. So you get all that space back. You shrink the applications back down, but you still have a processor that can natively address however many gigabytes of memory you want to put into it and so on. So most of the work in this area is to be done in user space at this point, getting libraries and all that stuff. But we do need to define an API with the kernel for processes running in this mode or this personality you can think about. This has been mostly done. The developers got distracted with other stuff and it slowed down, but I wouldn't be surprised to see sometime in this year some distributors starting to show some real interest in putting together an X32 version of their distribution. In August, we celebrated 20 years of Linux, of course, 20 years since Linux first came out, so they've got this little project. That line plot there is just the count of lines of code in the kernel over the course of 20 years. You can see a pretty obvious trend, right? Despite economic crises and whatever else went on over the course of these 20 years, the kernel just continues to grow. From its beginnings, the first kernel posting was about 10,000 lines of code, right? Tiny. And there's only one place where we ever got smaller, which is 2636, where we did some cleaning up, rid of a whole lot of defconfig files. And we made it smaller one time. It's the only time in the entire history of the kernel that this has happened. And I suspect that's a record that's going to remain unbroken for some time yet. Of course, the other sad thing that happened in August was the compromise of kernel.org. So, still piecing that stuff together. We know that the attackers have been on the system for some time before they were discovered. They got on using stolen credentials, and then they installed Trojan SSH binaries so they could steal more credentials and move on to other systems. As a result, a number of other systems were compromised as a result of this. As far as we can tell, there was no attempt to actually compromise the software distributed on the kernel.org systems. We would have caught a lot of it pretty quickly if they had tried to. In other places, it might have taken a little bit longer, but a really determined effort was made to find any attempt to compromise them. As far as we can tell, that's just not what they were trying to do. But the result of this was that we lost kernel.org for almost 2 months, which was kind of a pain, and that resulted in the delay of fit up on release and so on. So what's been done about this? Well, we have a new kernel.org. They basically tore it down and rebuilt it now with a bunch of new machines, split the functionality apart, hired some more staff so that we have a better handle on what's going on there, restricted access because it occurred to somebody somewhere along the line that maybe having 450 shell accounts in your master system is just not the best of ideas if you really want to avoid going through all this yet again. So we don't have that anymore. There's been a new web of trust for the kernel developers built around a new set of GPG keys and so on. A lot of the stuff was enabled through a lot of support from the Linux Foundation. It really helped out a lot with this. So we have a new kernel.org. Hopefully this is more functional and more secure. And hopefully we don't have to go through this again. But I'll say something that I've been saying for quite some time, which is we don't take security seriously enough. We just don't. The level of the attackers out there and their motivation is such that we're going to see incidents across the free software community. We've seen them in the past. We will continue to. We have to get more serious about this, and that's not going to be easy or fun to do. All right, moving on to September. One thing that happened in September was that Oracle said they would start shipping ButterFS by default. I kind of felt like I was being watched as I was reviewing this slide this morning, so I took a picture out my window. You really want to Photoshop in a red eye over there or something. But you know, what Oracle is doing with ButterFS is actually very good stuff. And what they're doing is they're pushing it. They want it to be the core of their enterprise distribution. So what's going on with ButterFS? Well, there's some new feature work happening with ButterFS, but ButterFS developers are very much focused on stability and getting this file system to the point where it is ready for production use. And the regions they're thinking about, Fedora has once again pushed back its plans to go to ButterFS by default. But this will happen sometime soon, and we will have people actually starting to use it. But there's some missing pieces. The biggest of one being arguably the file system checker, in particular the file system repair tool. Writing a file system repair tool is actually a very hard task because if you're not really careful, when you worse than it was before, and take data that might have been recoverable and make it unrecoverable. So this has been a very long-term project that's being done with a lot of care, and it's taking a while. In the meantime, they have added a couple of features, including what they're calling the root block history array. This is just an array of the previous states of the file system. ButterFS being a copy and write file system, essentially every previous state of the file system is a snapshot. So you save a few of those, and if something goes wrong and you catch it soon enough, you just go back to your previous state of the file system, and your problems go away. They've also written a read-only data recovery tool that can extract the data from the badly broken file system without making changes to it. So we have a lot of pieces there. The full file system checker is actually out there in the repository now if you look for it, but it hasn't been announced as being actually ready for anybody to use on a real file system. We're also missing the RAID support. The patches for that actually have existed for a few years. They just haven't been merged. That stuff will come around, and we'll see ButterFS stabilizing quite a bit, I think, over the course of the next year, and starting to go into real production use in some places. All right, October. October, of course, everybody was in Prague because that's where the action was, including the 2011 Kernel Summit. So we talked about a lot of stuff at the Kernel Summit here, but I really wanted to point out just two outcomes that I thought were sort of the key outcomes of this. One was a statement. This is not a new one, but we heard it again. The kernel maintainer should be saying no more often. That we take stuff into the kernel too easily, that perhaps shouldn't be there. We need to push back a little more and insist on really good reasons to get more code into the kernel, especially code that adds complexity. On the other hand, it was understood that code that is widely used out there, that has been widely shipped, should perhaps be brought into the kernel, even if it doesn't really live up to our technical standards otherwise. This was, of course, very much said with the Android code in mind. That it's been out there, it's been shipped to millions of people, and it's kind of silly at this point that we don't have that sort of stuff in the manual. So those are a couple of decisions that came out. Also, kind of a slow moment, actually, while he was sitting at a table at the Kernel Summit, Linux released 3.1 kernel came out. This was a 95-day development cycle, which was kind of longer than usual. But the reason for this, of course, was the kernel.org outage and the lack of a desire in particular to open up a merge window without having kernel.org there as a place to host a lot of trees. So we added various features, including dynamic write-back throttling, which is an attempt to solve our write-back problems. Write-back being just a process of flushing dirty pages of memory back to their backing stored disks, pages that have been written to files and so on. We've had performance problems in that area for a while. We've been trying to fix them up. Some of that stuff went in for 3.1. We got a new architecture, OpenRISC, which is actually an open source hardware design, and some improvements to the ptrace system call, the LC system call, various other things that went into the 3.1 kernel, which was released during the Kernel Summit. And one other thing that happened in Prague was the announcement of the Embedded Long-Term Support Initiative. So there are various aspects to this, including this concept that we'll pick one kernel a year and maintain it for 2 years going forward. This is just going to be part of the regular state of kernel process. And in fact, it's already happened starting with the 3.0 kernel, which will be maintained for a couple of years. There are a couple of other trees involved with this initiative aimed at helping the embedded and mobile communities standardize on a single tree and to get their code back up into the main line. Shibata-san, I believe, is talking about this later on today. So if you're interested in this, I would advise going to see his talk. This is a very welcome and very worthwhile effort, and I wish you the best of luck. All right, November. Something I want to talk about very quickly is the addition of per-group TCP buffer limits. This is a limitation on the amount of memory in the kernel that can be taken up by outgoing network data. And it's interesting because it's the first mechanism put in place to limit the amount of memory used by the kernel on behalf of user-space processes. This is something that there's interest in doing in a lot of other areas as well, in various caches and so on. We haven't had the mechanism to do that. We do have that now with with the TCP buffer limits. I was supposed to talk to you just a little bit about control groups in general. Control groups, of course, are just a simple mechanism for grouping processes into hierarchies and then allowing the addition of controllers to apply various policies to those groups. So developers complain a lot about control groups. They really hate them. But a lot of the real trouble is actually not in the control group mechanism, but in the controllers. We have these various controllers that manage things like memory usage, block I/O bandwidth, CPU scheduling, and a bunch of other stuff. A lot of these controllers don't necessarily integrate well, not only with each other, but with the systems that they're meant to be controlling. And that was partly by design because the people writing these controllers have tried to be very non-intrusive in how they did it. But it means that we end up with these sorts of works bolted onto the side of the kernel, implementing these controllers. So there's going to have to be some cleanup work done there. And what we really need is a central control group maintainer who can oversee all this stuff and keep heads together and make this stuff integrate better with the kernel and within itself. And then that hasn't happened yet, but I think that's going to have to come together sometime really soon. One other thing happened in November. The Linux Trace Toolkit Next Generation is a tracing toolkit with a whole lot of nice features, nice user space support, and so on. It's been out there for years and widely used in some areas. It was pulled into the staging tree with the idea that it would be merged with 3.3 kernel. And what happened was a big, long discussion that really recalled this discussion here. This is the same slide I put up before. Right? On one hand, people were saying maintainers are supposed to say no more often. We're going to say no to this one because it doesn't integrate with the existing tracing mechanisms. We don't like the way some parts of it work. We say no. On the other hand, people are saying, well, this is code that has in fact been shipped to a whole lot of people. It's widely used. This is something that we should bring into the kernel under this decision that we should bring in this sort of code. So people thought about it and all that. The end result was the Linux Trace Toolkit lost in this case. And it was kind of ushered back out of the staging tree. If you look in the kernel history, you actually see it in there for a little while, and then it goes away again. That functionality, if it's to get into the kernel, is going to have to be broken up and integrated with our existing tracing functionality. And I honestly don't know if that's going to happen to any degree or not. It's kind of a shame because there's some good stuff there. But it's a long story in working with the development community that hasn't been worked out well. December looks like in Colorado. We had an announcement in December of what was called the Android Mainlining Project. This was sort of the joining together of a couple of efforts that had been going on out there, reinvigorated by the decision of Kernel Summit, to try to get this kernel code merged. So brought together a whole lot of this stuff. In fact, I need to make one change already because one piece has already been shut back out, being PMEM, continuous memory allocation. We talked about that a bit on Monday for those of you who were here. But there are various other pieces to the Android system. There's a couple of pieces that aren't here yet, including the wake blocks and the analog memory management system. So a lot of this stuff has found its way into the staging tree. There's been some discussion of trying to move it into the mainline. There's been all the usual same old arguments all over again. We'll see how long that takes. But slowly this stuff is merging there. And as Greg will tell you, with a 3.3 kernel, you will actually be able to run the Android user space on a mainline kernel if you just don't care about little things like battery life. But we're getting there. This is progress in the right direction. So, January of 2012, we're coming around towards the end here. So, exactly 1 year after 2.6.37, once again on January 4th, we had a kernel release. This was 3.2. This was a big release with almost 12,000 change sets in it. Proportional rate reduction being a networking change to deal better with losses of data in transit. Extended verification module is a trusted computing mechanism. It's meant to defend the files on your system from offline attacks. You can detect if somebody has been messing with things. We got a new controller for the control system for control groups for CPU scheduling, where you can now say this group of processes never gets more than 10% of the CPU, even if that CPU time is available because they're not paying for it. Cross-memory attach is an inter-process communication mechanism. We got the hexagon architecture, architecture. The BFS root block array that I mentioned before went in, and a thing called IOLS dirty throttling, which is a rather complex application of control systems theory to the write-back problem, trying to balance the level of dirty pages in the system with what the backup store devices can do, and keep the dirty pages from overcoming things. It looks like good code, and I think most people who can actually understand it really approve of it. For the rest of us, we'll see. We also had the 3.3 merge window in January. This is the merge window for the upcoming kernel that we will see sometime in March. A lot of networking stuff went in for 3.3, including the team devices as a lightweight bonding device that went in there. Network priority control group, actually controlling access to the outgoing interfaces based on control groups. TCP buffer sizes, as I mentioned before. Byte queue limits are an attack on the buffer bloat problem. We're now putting in limits on the amount of data that can be queued to any outgoing interface, trying to keep from buffering too much data and messing up with our protocols. And Open vSwitch is a complex new virtual switch used in the virtualization area. It actually holds up the potential for other interesting flow control types of applications and so on. People aren't doing that yet. Outside of networking, we also got support for large physical address extensions in the ARM architecture. So now you'll be able to put more than 32 gigabytes of memory into a 32-bit ARM system. And we're going to have all the same kind of ugly stuff that we've had that take 6 in that area. But, people want to do it. The Android drivers return, that I mentioned before. We got the DMA buffer sharing API, so we can under user space control, share buffers between different devices. Attack on the hardware capacity problem. And a whole bunch of other stuff went in for 3.3. That is going to stabilize things, like I said, sometime in March. We're going to see that particular release. And that brings us around to right about now. And there's really only one thing I'm going to mention, which is that Brady Hartman, as I joined the Linux Foundation, will be able to work on stable trees and such as something closer to a full-time job. Although one wonders, because if you look, one of the first things he did was actually start submitting patches to LibreOffice. Which may not be what the Linux Foundation had in mind, even though it's a worthy cause for sure. But this is a good thing. This will help to beef up our work that is done on the stable tree. And people who watch the work he does wonder how it is that he gets all this stuff done. So hopefully he'll have some more time to do that. So there's a whole lot of other things that I could have talked about. Even though I have kind of talked along with the ground over the course of the last hour. But I'm not going to do that. Instead, I think what I will do is I will stop here, and I would be happy to answer any questions that people may have. Somebody must have a question. All right.